Yeah, it's Julie here. Welcome back to Advanced C++ Tutorial 5. We have finally reached the last tutorial of the math arc of Advanced. And after this one, you're going to be ready for 3D fundamentals, and we can actually start doing some C++ in Advanced C++. So today's topic is matrices. Something something, the one, something something, there is no spoon. What if I told you something something? You get the idea, right? Why did the Wachowski brothers call it the Matrix anyways? Well, why did they make any sort of creative decisions? It's because it looks and or sounds cool. And yeah, matrices sound cool, they seem complex, but really they're not that complicated. And in this tutorial, I'm going to teach you what they are, what they do, how they do, and why we need them. So the first question is, why matrices? Well, matrices are just a tool that allow us to encode our transformations in an elegant and uniform manner. So right now we build up our rotation angle, translation coordinates, and scaling factor separately, and then we apply them separately to the vertices. And matrices are going to replace that with a single thing that you can apply to every vertex. You know, I used to think that the matrix was some kind of dark magic at the heart of 3D graphics. If I could just understand matrices, I could unlock the secret of 3D. But technically, matrices aren't essential for 3D. You can do 3D without them. They're just an elegant, convenient notation or structure. But since pretty much all APIs and graphics hardware are designed around matrices, in practical terms, they are essential for doing hardware-accelerated 3D. So, in other words, you gotta learn this shit. Alright, so what is a matrix? Well, whenever I'm trying to figure out what a noun means in English or Japanese or German, I usually just do a Google image search. Picture's worth 1,000 words, right? So these are matrices, mostly. And you can see they're basically just arrays of numbers. That's all a matrix is. It's a two-dimensional array of numbers. You've got rows and you've got columns. And there you have it. That's really all there is to it. Well, not really, but we'll get to that in a second. Now, in general, matrices can have, any dimensions you want. You can have a 2x3 matrix or a 1x3 matrix or whatever. But for us, we're only going to be working with square matrices. So only with 3x3 or 2x2 matrices. That's really the main kind of matrix that you're going to run into when you're doing graphic stuff. Now, if a matrix were just defined by its format, it would be, it'd be a big whoop. I mean, it's just an array. It's like if you're a janitor and you call yourself a sanitation engineer, it's still the same thing. But a matrix isn't just defined by its form, it's also defined by the operations that you can perform with it. Now, the most important operation is the matrix by vector multiplication. So you can apply a matrix to a vector, multiply it, and the result is going to be another vector of the same dimensions. So what a matrix actually does is it defines a transformation that you can apply to a vector. So let's see how you actually do that. So to find the value of the first element in the result vector, we're going to multiply the first row of the matrix by the vector, and we're going to sum those results. So what we're going to be doing is we're going to be multiplying 3 times 2, which is 6, plus negative 6 times 3, which is negative 18. Now we're going to do the same thing for the second element. We're going to go now, since we're doing on the second row of the vector, we're going to use the second row of the matrix. And we only have one column to use in the vector, so we're going to use that one again. And it is 5 times 2 is 10, plus 1 times 3 is 3. And then you add those up and you get the result of negative 12, 13. So vector v multiplied by the matrix A is equal to negative 12, 13. In general, the notation for matrices is a capital letter, often rendered in bold. All right, let's try one more. This time we're going to do a 3x3 matrix times a 3-component vector. So the result is going to be, for the first element, you got 1 times 1 is 1, plus 4 times 2 is 8, plus 0 times negative 2 is 0. Second element is negative 2 times 1 is negative 2. 0 times 2 is 0, and 3 times negative 2 is negative 6. Last element, 3 times 1 is 3, plus 1 times 2 is 2, plus 2 times negative 2 is negative 4. And there you go, there's your answer. Not too difficult. I hope it's not too complicated once you visualize it like this. You're just multiplying the rows of the matrix by the column vector for every one. That's all there is to it. Now notice that the number of columns in your matrix have to match the number of rows in your vector, otherwise shit's not going to line up like this, right? So they got to match. In general, our matrices are all square, so all you got to know is that if you've got a 3 by 3 matrix, you need a vec 3. If you've got a 4 by 4 matrix, you need a vec 4. 2 by 2, you need a vec 2. Simple. Now we can see here that this matrix corresponds to a transformation of some input vector to some output vector. Every row in this matrix corresponds to one element in the output vector. And what each row is doing is it is multiplying, it's taking x, y, and z into account, multiplying by different factors, adding the results together, and that gives us our new output. So this one takes x, y, z into account and generates a new z. This one takes x, y, z into account and generates a new x. Now at this point, before we move on, I'd recommend maybe, if you're not familiar with matrices, take 30 minutes or so, Google some problems multiplying vectors and matrices, and look through the results. You might find a page like this, and it's going to show you examples here. So what you can do is you can, don't look at the answer. Try to multiply this out by yourself. Just try to find problems where you're multiplying a vector, column vector, by some square matrix, and try to solve it. All right, so hopefully you've taken some time, you've done some pen and paper calculations, and now you're familiar with the mechanics of multiplying a vector by a matrix. Now, let's do some code. Let's code up a matrix class. So we're back into the code base that we've been using for advanced, the star field, and we're going to make a matrix class. So we're going to create a basic mate2 class. It's going to be templated, just like we did for vec2. Now, first thing, what kind of data are we going to store? Well, matrix is an array of numbers, so let's store it as an array. And we're going to do something a little different here. I don't think I've done this yet, even in beginner. We've just been using flat arrays for everything and then calculating. If it's a two-dimensional array, we calculate the x and y indexing ourselves. But let's use the C notation of, let's call this one, we'll call it cells. And let's use the C notation of having an array of arrays. So it's going to be a 2 by 2. So here, first thing first, and this is one of the reasons why I don't tend to like to use these that often. But one of the main things is that it's easy to get mixed up which one is the row, which one is the column. And the way it is it is row first, then column. So if we look at a little bit of help here, we've got a matrix we define here, 0, 1, 2 in the column. That's going to look like this, 1, 2, 3, 1, 2, 3. And then the second row is going to be 1, and 4, 5, 6, 4, 5, 6. So that's the way it maps, and you just got to keep that in mind. But this allows us to make it public, and we don't have to add setters and getters for where you pass in a row and column and it sets the thing. We'll just make the whole thing public, because that's what we did for vector. We just made x, y, and z public. So we're going to do that for matrix as well. So now we have the data. We need to define the operation. There's really only one operation right now that we want to define. That's multiplication by a vector. So the standard notation is matrix times vector gives you another vector. So matrix is going to go first, and that means we probably want to put the operation in the matrix class, which is nice. That coincides with my plans very nicely, and it is going to return a vector. Now we want the types to match, so we're going to template our vec2 on the same template type as the matrix. That's the return value, and we're going to go operator multiply, and parameter is going to be another vec2. Const function doesn't change the matrix to multiply it by a vector, and now we've got to do the multiplication. So the idea is simple. In the major axis, the main loop we're doing, the outside loop, we're looping through rows here, right? We're applying each row to the vector. So that's the outer loop. In the inner loop, we're looping through every column in the row and multiplying that by every row in the vector, or every element in the vector. So outer loop, looping through rows from 0 to 2. Inner loop, going to be looping through columns. Now we want to multiply the values in the matrix row by the vector values, and we want to do a sum. So we're going to go t sum is equal to 0, and then for every column here, what we're going to do, and here we run into a bit of a snag, because what we want to do is we want to go v at column. For multiplying, if column is 1, that would multiply this one by this one. The only problem is our vectors don't have a way of indexing them by number, only by x and y, x, y, and later on when we do a vec3, it'll be x, y, z. But unfortunately, we can't do this. So what are we going to do? Well, we have two options. We can cheat. We can reinterpret the first element of the vector as an array of floats, because those floats are in a struct, in a class in memory, and they're all lined up in memory. So we can reinterpret it as an array, and then we can index into it, and that will work. But technically, it's undefined behavior according to the C++ standard. You're not allowed to interpret between two types like that. You're only allowed to cast from any type into a car pointer. So we could do that, it would work, but we're not going to. Instead, we're just going to manually multiply all these guys out. So how does that look? Well, let's create our output vector, first of all, vout, and then we want to do vout.x is going to be equal to, and we're multiplying the first row of our matrix by our input vector. That's going to look like this, right? Cell 0, 0 times Vx, cell 0, 1 times Vy. And then we do the same for y. 1, 0 times x, 1, 1 times y. I think I'm going through puberty, but that's okay. Second puberty never hurts anybody. Return vout. We could have done this all in a single one-liner, but it doesn't matter. It's going to all compile to the same machine code in the end. So there you go. There's your multiplication. It's very simple. For 2 by 2, even without a loop, it's not going to kill us to write it out like this. All right, so I got a little matrix multiplication calculator thing on the web, and I put in a little test matrix. It gave me this result. Now let's test that against our code. So we're going to go into game.cpp, and we're going to include our matrix multiplier, me2. And let's see, what are we going to do here? We could just examine the result with the whatchamacallit, the debugger. That way we don't have to worry about trying to output somewhere. So we go mate2 float, and we'll just call this one m, and that's going to be equal to, what is our matrix values again? 1, 3, negative 6, 0. So 1, 3, negative 6, 0. And our input vec2, and that's interesting. Probably should have used the same naming. Yeah, let's do that right now. So this is going to be underscore mate2, and then we can do using mate2 is equal to, last time I did a type def, this time I'm doing using. It's all the same in the end. Using is a little sexier. Using mad2 is equal to mate2 of double. You get the idea. Again, this prefixing your types with underscore is not a good idea, but it's what I've started with. That's what I'm going to go with. It's not going to hurt anything, but in general, don't do it. Anyways, so we got mate2, so we don't need the float there anymore. We got vec2, and that's going to be negative 4, 3. And let's do auto. W is equal to m times v. Put a little breakpoint there. So we got our vector, or our matrix m, 1, 3, negative 6, 0. V is negative 4 and 3. And when we step over this line of cone, W is 5, 24. 5, 24. Easy money, right? Easy money. All right, so we've got our matrix type. Matrix multiplication works. But what can we actually do with this? Well, like I said, matrix multiplication, a matrix actually maps a transformation that you can apply to a vector. So we've got transformations that we are doing, scaling, rotation, etc. Let's try to encode those in a vector form. So for scaling, it's very simple. You multiply some scalar by a vector. That's going to multiply both components of the vector by the scalar. So how do we encode this in a matrix? Well, it's going to look something like this. It's going to be S, 0, 0, S. S is going to lie on the diagonal. And try it out. Try multiplying this against a vector. Well, the result is going to be this times this is S times X plus 0 times Y, which is just 0. And this one is going to be 0 times X, which is 0, plus S times Y, which is S times Y. There you go. This is the encoding. This is how you make a scaling matrix. You just put the scaling factor on the diagonal. Little side note, scaling by 1 does nothing, right? Just you get the same thing back. If you put 1s on the diagonal, you're going to multiply 1 times X, X, and 1 times Y, Y. It does nothing. It leaves the vector as it was. We call this special matrix the identity matrix, because that's not how you spell it, but whatever. Because you multiply by something and you get that thing back. It's the same as in scalars, multiplying anything by 1 has the same value. So, this is a special matrix. We call it the identity. It's useful sometimes. This is a scaling. Let's add some functions to mate2 to generate those guys. So we'll make a static function called scale. You pass it a scaling factor. And well, let's just call this one factor. And it will return a matrix that gives you a scaling of that factor. And that'll look something like this. I just line things up so it looks more like a matrix in the code. And you can do the same thing. You can make static mate2 identity. And that's just going to be return scale of 1. But 1 type t. Now another kind of transformation that we often find ourselves doing is flipping the y. So let's make a mate2 flip y because we need it. And that is going to be, well, we can't call scale for that. So we'll do that. And it is going to be, x is going to be 1. We keep x the same. But y is going to be negative 1. Now I just figured something out here. You got to make sure that you template, you cast these guys to the type. Otherwise, you're going to get warnings in your compiler. Probably. So we want to make sure that those are of the type T. And we want to also make sure that these guys are of type T. So let's do that, and that, and that, and that. And there you go. Beautiful. So this one will flip your Y for you. All right, now the last transform we're going to do is the rotation transform. And so we go back to what we did in tutorial 4, I believe. And we see that X is going to be equal to X times cos phi minus Y times sine phi. And Y is equal to X times sine phi plus Y times cos phi. So now we copy this into here. And what we're going to notice is that the transformation for X is going to multiply X and Y by some things. And transformation for Y is going to multiply X and Y by some things. That's what our matrix does, right? So we got an input. Let's take our, these guys. This is going to be Px, Py. Output X is equal to Px times cos. We're going to use theta, because I like to use theta usually. So Px times cos theta minus Py times sine theta. So we put a negative in there. And y is going to be px times sine theta. So that's sine theta. Px times sine theta will be here, plus py times cos theta. Cos theta. And there you go. You've got your mother freaking, this is the rotation matrix. That's how it's derived. That's how it's encoded. That's how all the good stuff is done. Now all we gotta do is make a little funky for that. So let's make our matrix rotation. We're gonna pre-calculate cos theta and sine theta so we don't duplicate any work. And we do the same for sine, and then we just gotta fill those bad boys into here. Alright, well I immediately see some problem here. Here it is. We're missing commas here, here, here. Probably good to nip that in the bud right there. But there you go. Now we've got all the transformations that we want. You might be saying, Chile, aren't you missing one? We'll get to that in a second. But for right now, these are the ones we want. Now, let's test them out. Now, one little small point here. The name of the templated type is actually underscore mate2. So this ain't going to compile if we try to compile it. So let's fix that. Now, what I've done here in game.cpp is I've commented out the Starfield drawing code. And I've just created every frame. We're going to create a star. We're going to create a transformation. We're going to apply that to all of the vertices of the star. And then we are going to draw the star here. Create a drawable from the star and a color. Draw that shit to the camera. So if we do this, we should expect a 100 radius star to be scaled up to 150 radius. And I mean, that might be true. Let's change the scale, see if that changes the size of the star. So let's go down to 0.5. I'm going to make it small. Run that, and it seems to be working. So our scaling via matrix works fine. We just apply that matrix via multiplication to each vertex of the star model. We could change that to a rotation. Here we're going to apply a counterclockwise rotation of, I believe, 0.3 radians here. And that's going to look like this. If we did not apply the rotation, so let's change that to 0 radians. We run that. We see it's in a different orientation. So the rotation is working fine. We can also apply multiple transformations here. So we're going to rotate, we're going to scale, and then we're going to flip the Y. We're going to apply them by consecutive multiplication here. We run that, and you can see here, it was rotated so that the point was here, and then it was flipped in the Y, and it's also been scaled up. It's very big now. And there you go. There is the basic idea of encoding transformations in a matrix and then applying them to a sequence of vertices to transform some model. Now let me show you something that may or may not blow your mind. So we can actually multiply one matrix by another matrix as long as the dimensions match up, and that will give us a different matrix. So a matrix times a vector is a vector. A matrix times a matrix is a matrix. And for us, the rule is simple because we only use square matrices. And you just have to make sure that the dimensions match up. So if you got a 3 by 3, you want to multiply it by another 3 by 3. If you got rectangular matrices, rules are a little more complicated, but it's not that hard. But I'm not going to talk about it because it doesn't matter. We're only using square matrices. So how does this work? Well, it actually works pretty much the same as vector multiplication. So for the first matrix, you're going to go through by rows. And for the second one, you're going to go through by columns. But now you've got more combinations of rows and columns. So take any combination of row and column. Let's take the first row here and the second column here. That is going to what do you think that is going to yield in the result? Well, it's actually going to yield, let's just take this one here, draw it as a ghost in this matrix. You see where they overlap right here? That is where the result is going to go. What about these two? Where do you think the result is going to go from the multiplication and sum of this one by this one? It's going to go right here, right? Because that's where they overlap. So let's do this quickly. At least let's do one row here. So this one times this one. What is it going to get us? Well, it's going to go here, and it is going to give us 4, 0 times 3, 1 times 0. So it's just going to give us 4 plus 0 plus 0. And the next one, let's go here and here. Again, it's going to be 12 plus 2 times 3 is 6, plus 0 times 0 is 0. And then this one's going to be 0 plus 3 plus 0. 0 times 4, 1 times 3, 2 times 0. And then you start again with the second column here. Hopefully you get the idea. If you don't, I recommend you just do a little Google search. There's tons of videos and animations and stuff online that you can look up, and you get a handle of this. Either way, I recommend that you look up some problems online and do a couple of these on pen and paper yourself before you continue. All right, hopefully you've got matrix by matrix multiplication under your belt. You've done a few problems yourself. You're confident that you can work it out on pen and paper. Now let's translate that into code. So, matrix by matrix is going to output a matrix. So, mat2, well, we don't have to put the T in there, do we? Operator star. It's going to take another mat2 on the right-hand side. It's going to multiply them together. And so we start off by creating a matrix. That's going to hold the result. And we're going to start by looping through the rows of the left-hand matrix. And then for every row in the left-hand matrix, we have to multiply it by a column in the right-hand matrix, by all the columns in the right-hand matrix. So this will give us all the combinations of rows and columns. That's all these guys here. This guy times all these guys, this guy times all these guys, this guy times all these guys. Now we need a loop that pairs up the elements in each row and column. So we need a loop that's going to multiply this guy by this guy, this guy by this guy, this guy by this guy, and sum them all up together within each combination of row and column. So we're going to call that loop variable just I, and here's where the magic happens. So for every combination of row and column, first thing we want to do is we want to initialize the corresponding cell in the output. So the corresponding cell is the row left times, or not times, but and the column of the right gives us the corresponding output cell. And we want to initialize that to 0 because we're going to be accumulating into that in this loop. So what do? Well, output, which is again this boy here, accumulate into that cells, which is the left-hand dude, and row left. It's the current row that we're looping through, and then I for the column, because we're looping through the columns of that row, times right-hand side dot cells, I, because we're looping through the rows of this one, and column left. That's going to be static for this inner loop here. And there you go. That accumulates that into that, and we do that for all the combinations, and you've got your matrix. Don't forget to return out. And that should work. Now, might as well define a little happy time here. Don't know why I call it that. Doesn't really make any sense. Operator, multiply and assign, so you can multiply and assign to an existing matrix. And that's just going to be this boy here again. And all we're going to do is return this is equal to this times right-hand side. And that should work. And now we can multiply one matrix by another matrix. Let's try it out. So let's go const auto tform cat. And that's going to be equal to tform 3 times tform 2 times tform. I'm going to multiply all these matrices together, and we call this concatenation of the matrices into one single matrix. And we're going to multiply tform cat to all the vertices. So instead of applying tform, tform 2, and tform 3, we're just going to apply tform cat, which is all these guys multiplied together. Well, we get a build error because obviously, I messed something up here. And what I messed up, out. So yeah, I can't do this because out doesn't define these. We want out.cells is equal to that, and we want out.cells. Try it again. Let's go back. No. Column left is undefined right, because it's column right. It's column right though. Okay, please work now. And we get what do we get? We get the same thing that we got when we multiplied all the matrices individually. So let's do a recap. Before, we had to multiply each vertex in the model by matrix, different matrix. But if we concatenate them all once ahead of time, we can basically cut the amount of work we have to do down to a third. We only have to multiply now one matrix. And this matrix here, this T-form cat, this concatenated matrix holds all the transform information for these three separate transforms. These three transforms are all fused together to make one super transform that does all their work in one shot. And that is the beauty of using matrices for your transformations. You can jam, just knock down my drink. You can jam all the information together into a single matrix, and then you can apply that in one fell swoop to each vertex in your model. And if that doesn't make your dick even just a little hard, I'm sorry to say this, but you might have to see your doctor. You might have to get some Viagra or some Cialis. You might be suffering from a little bit of the ED. I'm just saying. Now, one thing you guys might be wondering, or what you should be wondering, is, well, okay, you got rotation, you got scale, you got flipping, that's cool. What about translation? Translation is basic. It's like the most fundamental transformation we have. It's the first one we learned. We learned how to translate the reticle. Where is translation? And, well, remember when I said that translation is a fussy little bitch? Well, I wasn't kidding about it. I meant it. You can't fit translation into this system that we have at the moment. But stay tuned. In the next video, I'm going to show you how we can get translation into the same matrix as rotation, scaling, flipping, a whole bunch of other bullshit. It's going to require a little extra work, but it's going to be worth it. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more advanced C++.